So what sometimes happens in practice is you look at a figure like this, and then you say, let's try out breakpoint test here, 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 and at some kind of point, yeah, well, maybe at some point you will reject, right? So do not, so the warning here is, do not data sneak, right? Do not look at the relationship and then say, look here, here's something strange happening. I don't know why, but let's test whether that's really strange. Yeah, of course, it must be. You have just looked, you have just spotted that there is some break. Yeah, no surprise if you test and yeah, there is a break, right? The idea is, from an economic point of view, that that approach makes only sense if you first have a theory for your hypothesis, and then you go to the data, right? Then you can apply the child breakpoint test. Of course, if you present in your season or whatever a breakpoint in 1994, in 1997, in I don't know when, right? There was always a good story, you know. It's just, you know, it's up to you to make a story up. You know, every year something strange happens. Okay? So, and that's the danger, right? So you estimate, yeah, you will show, you know, your interesting contribution to literature is to show that the well-known linear relationship between x and y is actually not linear. There's a break in, I don't know, 1994, right? And then you argue, yeah, because in 1994, I don't know what happened. And that is the reason why there is a break. Okay. So, question, how to defend or how to make up, how to encounter the problem that you run all these Chow tests and and one, and here is significant, and therefore I reject another hypothesis of linearity. So how to encounter the critique that this significant test result of a break in the linear relationship is just the consequence of data snooping. More than one observation. Now look, you have a time series from 1950 until today, right? And then you run these regressions here, you know, and allow for a breakpoint in 1955, 1957, 1958. You run a sequence of Chow tests, right? And what I'm saying is, even if the true relationship is linear, you will find at some point of time a significant value of the Chow test, just because of random variation, right? So this is what I'm just talking about.
But I'm wondering if it's like, would the test say, yeah, there is a breaking point?
Yeah.
If it's like only this one observation, which lies like outside, which is in the rejection area.
Yeah, look, the
should be like all other variables coming after, or should also be.
Look, you have, if you have, so you have something like that, and then you have an outlier. Yeah, you're talking about outliers. Okay, so outliers, you know, are always a problem for least square estimation. We talked about that already, right? For the Chow test, not a particular point, right? Because if you what you do in the Chow test is you divide the sample, right? Here's T0 or what, right? And then you estimate it for this subsample and then for that subsample, right? And of course, you know, the Chow test might have hiccup, right? When there's an outlier, but still, you know, if you estimate until here, it's just one point in a big sample. So one outlier should not drive the result of Chow breakpoint test. Yeah? Try it out.
But then why is there a PI? Why is it XI?
Yeah, because this is just saying that I run, so here, formulation is, because this is not a time series data, I order the observations with respect to the size of xi. And the idea here is the linear relationship here is different when xi is smaller than the average. This is just the example here. Because then this is 1, and then the linear relationship is beta plus gamma, and if gamma is, say, positive, then it is steeper for small values than for large values, right? And this is easily tested with a t-test here in that example. Okay, if I have more observations, more regressors that might break, it would be an F-test. This is how that test works, but it's just an F-test or a t-test, whether some coefficient changes. All right? Yeah.
So yeah, this I was actually thinking about, because for me it's just a nested model. Like we first
The
have
linear model is nested.
yeah,
Yeah,
right, and then
right.
we could basically apply ANOVA, which is just a F-test.
Yeah, correct.
So we
Yeah.
don't actually need the normality of the errors, do we?
You need the normality of the error to have, even in small sample size.
On small sample size, but with the
yeah.
asymptotic normality of the
Of course, if you have a lot of observations, then this is asymptotically, you can apply likelihood ratio test or whatever you want.
I was just
Okay?
curious about the normality.
But this, these are the details. These are technical details. What is more important for you as an economist that want to work with data and draw conclusions from empirical applications, blah, 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 is how to interpret, how to apply this. And let me go back to my main point here. Okay.